So last time we talked about the idea of two equations and two unknowns. We're going to be building up so we can do more equations and more unknowns. And we're going to be building up the machinery that lets us do it a little bit more systematically, a little bit easier bookkeeping. But let's still practice our two equations, two unknowns. And in particular, practice translating from words into math. I know a lot of people aren't big fans of word problems, but the thing is, the world around us is full of words. We have to learn to accept that. And so we have to think, how can we translate our world into mathematical language that lets us understand and solve things? So here's a problem. A fruit grower uses two types of fertilizer in an orange grove. So there's brand A and brand B. Now, the way this is written, it really helps distinguish things. So it says, well, what's going on with brand A? Well, there's 8 pounds of nitrogen per bag and 4 pounds of phosphoric acid per bag. And both of these things are very useful if you want to grow things. On the other hand, brand B, slightly different mix. So they have 7 pounds of nitrogen per bag and 6 pounds of phosphoric acid per bag. So it's more balanced in some sense. So what needs to be true? Well, the orange grove needs 720 pounds of nitrogen and 500 pounds of phosphoric acid. So the question, how many bags of each brand does the farmer need? Now, if nothing else, we should at least say, hey, there's some numbers here. Those will probably enter into our problem. So we have the 720 pounds of nitrogen and 500 pounds of phosphoric acid. So what's going on with this problem? Well, we have to decide how much of each brand to get. So there's, I was talking last time, there's like knobs. And we can set each knob according to what we need. So in our case, our knobs are like, well, how much of brand A do we buy? And there's the second one, how much of brand B do we buy? And we're trying to somehow combine that together. So, what's the key? Well, we have our nitrogen needs, and so let's talk about that. Now, we need some names for variables. Now, we can choose any names we want. We could go X, Y, but I think that there's a fairly convenient set of names. So let's have A equal the number of bags of brand A. And let's let B be the number of bags of brand B. This has the convenience of helping us just say instantly, yes, I understand what A and B represent. So let's start with the nitrogen. If we buy A bags of brand A, there's 8 pounds of nitrogen per bag. Altogether, how much nitrogen are we getting from our purchases from brand A? A bags, 8 pounds per bag. We get 8A. Similar question for the other brand. Brand B. We're buying B bags of brand B. There's 7 pounds per bag. How much nitrogen is coming from those bags? The answer? 7B. Now, how much do we need? 720 pounds. So, we need to choose A and B, so that 8A plus 7B is 720. We'll do the same thing with the phosphoric acid. All right, so for phosphoric acid, we again say, okay, we bought A bags. There's 4 pounds per bag. So the total amount of phosphoric acid coming from that part is 4A. For brand B, we have B bags, 6 pounds per bag. So that makes 6B. How much do we need? 500. All right. So we have our 2 equations and 2 unknowns. So our unknowns are the A and the B, and our equations 8A plus 7B equals 720. 4A plus 6B is 500. Now we're going to use our tools from last time. We probably won't graph, because graphing can be really hard to nail down unless you have a very good grid and a very good graphing tool. And for me, even drawing a straight line can sometimes be a challenge. Okay, so that leaves us with a substitution and elimination. Now, I like to use elimination. And that's going to be, in some sense, where we're going for the next couple of lectures. So I look at these and I say, well, is it easier to knock out the A's or the B's? And so what is it we're looking for when we ask that question? We're trying to somehow combine these 2 equations so that when we put them together, we cancel one of the variables. We eliminate a variable. So, would you rather try to cancel an A or try to cancel a B? A. A looks pretty safe in this because what's in front of the A's are close. 8 and 4. What's in front of the B's, 7 and 6, not quite as close. So for instance, if we were to take the second equation and we're to multiply this by 2, and what would we get? 8A plus 7B equals 720. Maybe let's multiply by -2. Minus 8A minus 12B equals minus 1,000. Because if we multiply the whole equation, everything on both sides by the same amount, it's the same formula. Now, we add these up, and what happens to our A's? They're gone, they cancel. Oh yeah, you betcha, 7B subtract 12B, minus 5B. 720 subtract 1,000, it's minus 280. Don't worry, we have calculators for these kinds of questions. Well, 2 minuses, you can turn them into pluses. So we get 5B equals 280. So how do we get B? 280 over 5. And you pull out a calculator or other such device. Beep, 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 beep. 56. All right, so that says we should buy 56 bags of brand B. Are we done? No. What's missing? The A. Oh yeah, A, you betcha. We gotta get A. Okay, so how do we get the A? Well, we have the B. So we come back to a formula that uses both A and B. It doesn't matter which formula you pick. So maybe let's do this one because the numbers look a little bit nicer. So if we take 4 times 56 plus 6 times B, that equals 500. So we're using this information in one of our formulas. 4 times 56, also known as 224. So 224 plus 6b equals 500. If you subtract, that says 6b is 276. All right. And we divide. So 276 divide by 6. Well, our calculators can probably tell us that. It's 46. Ah! Ha ha ha! It should be. Thank you. Thank you for catching my error. Well, same process. So let's do it now correctly. 4a plus 6 times 56 equals 500. 4a, 6 times 56, that's 336. Good you caught that. Otherwise, we wouldn't have as good of oranges. Okay, 500 subtract 336 is 164, I believe. Everyone's saying, yeah, sure, okay. And 164 divided by 4 is 41. All right, there we go, 41. All right, so we should get 41 bags of brand A. Now, of course, these examples are oftentimes somewhat made up. Realistically, lots of things could have happened. One of the things that was very likely to happen is you wouldn't have ended up with whole numbers. And farmers have learned to deal with this. It's called using part of a bag and storing the rest for next year. But the process is the important one. All right, any questions? Okay. Well, quick thought for the day. Not a quote, but this is something that's very useful to note, which is if you want to make progress, and to be able to make progress, we must learn how to handle being uncomfortable. If you're always comfortable, say in your courses, you're not learning. You're not being stretched. You need to be challenged. You need to have some adversity. And that's how you grow. Some stress is good. I will say, of course, too much stress is bad. You have to learn to be realistic. But you should not always say, I don't want to be uncomfortable. No, it's okay to be uncomfortable. That's good for you. Now, what's our goal for today? We're going to be talking about matrices. And in particular, we're going to talk about augmented matrices. And mostly this is a way for us to do better bookkeeping. And so we're going to solve our systems by row operations on augmented matrices. And what we're going to see, it's the same thing we've been doing in Spirit. It's just a matter of how we keep track of what's going on. So that's where we're going today. And I will say matrices are going to play a big theme for the next, I think, 2 weeks. So it's we should get good at them. All right. Well, what is a matrix? Sorry, I got too crazy with my doodling here. A matrix, oftentimes we introduce and we say, it's an array, and we put numbers in there. And that's not wrong, per se, but it doesn't capture the full spirit. So it is true that you can think of it as there's a grid, you have entries, and for what we're doing, we're going to look at numbers. But it's more than just a collection of numbers. It's more than just a spreadsheet. I like to say that a matrix is an array with benefits. Now you might say, well, what do you mean by benefits? Well, what we're going to see is that when we use matrices, we're using them in a very particular way. In other words, matrices represent something. And by understanding what they represent, we can get power in how we use them. And so we're going to be doing lots of things with matrices. The benefits are going to come later, maybe towards the end of next week, the week after that. But for now, we say, okay, let's start. We have here a matrix that has 2 rows, 3 columns. So we use R's for the rows, C for the columns. So 1, -4, 5, 7, 3, 6. We have the individual entries. we denote these as A, I, J, and just that says what's the entry in the ith row and the jth column. We'll talk about the size of a matrix, and the size is how many rows and columns are there. So we say it's the number of rows times the number of columns. So this is a 2 by 3 matrix. And we will say in a few lectures, we love square matrices, because we get to do a lot with square matrices. Now, what's a square matrix? That's where number of rows equals number of columns. So like 3 by 3, 4 by 4. You can do a little bit more with square matrices. All right, so that's just the matrix. This, for right now, at our very basic level, we're storing numbers in there. Next, we're going to look at what we call an augmented matrix. And essentially, we're just going to take a matrix, add an additional column on the end. And we're going to separate it with this divider. So essentially, it's like we started with the matrix, and then we added on. So that's the augmented part. We've added something on. Now, why are we going to use augmented matrices? Well, we're going to use them to store our system of equations. So if I have two equations, let's say, we'll go with our example here, x, which you'll think of as 1 times x, minus 4y equals 5, and 7 times x plus 3y equals 6. We say, well, what really matters? Well, it's the coefficient. So we're storing the numbers. So you'll see we have here this dividing line. We'll think of this line here as it's like the equals line. So the 5, 6, that goes into 5, 6. And then the coefficients of x, that becomes one of our columns, 1, 7. The coefficients of y's becomes another column, negative 4, 3. And also, it's important to note that each row is an equation. So we're not just jumbling up randomly. Each row is an equation. Each column to the left of the dividing line corresponds with one of the unknowns we're trying to solve for. The column to the right of the dividing line, that's the right-hand side of constants. And so we can put in a system of equations into an augmented matrix. Of course, we can go the other direction. If we have such an augmented matrix, we say, oh, this corresponds to a particular system of equations. All right. So, what are we going to do? Well, let's go back to what we talked about last time. So last time we talked about elimination. And before we got into elimination, we said, there are 3 things that we can do to our system of equations and have an equivalent system of equations. And we're going to translate that into the language of these augmented matrices. So let's remind ourselves of what those 3 things are. One thing that we said is we can swap equations. So let's actually go ahead and remind ourselves. So we had our x minus 4y equals 5, and 7x plus 3y equals 6. I'm just copying this from the last page, and this is our augmented matrix. 1, negative 4, 5, 7, 3, 6. So when we talk about swapping the equations and versus swapping rows, well, here, swapping the equations means it becomes 7x plus 3y equals 6, x minus 4y equals 5. And what happens? Well, again, just read off the coefficients. You get 7, 3, 6 in the first row, and 1 minus 4, 5 in the second. So you swap the rows. That's swapping the equations. Still the same system in respect to the solutions. Any solution that I had before remains the solution Any new solution was also an old solution. All right. Well, we can denote this by just saying, hey, swap rows. So row I is trading places with row j. In this case, we would say, this is row 1 is swapping places with row 2. Now, another thing we said is we can scale an equation by a non-zero constant. So, for example, if we come up here, I could have multiplied the first row by a 3. Why not? I mean, I could have multiplied it by anything. So it becomes 3x minus 12y equals 15, and 7x plus 3y equals 6. Well, again, read off the constants. You get 3 minus 12, 15, and 7, 3, 6. So what's going on is scaling an equation by a non-zero constant. That scales the row by a non-zero constant. Now, here I will say I wrote my notes up before I closely checked what the book uses for notation. And so it turns out the book flips the arrow from what I wrote. So I like to think of it as row I becomes some constant row I, and the book likes to say it the other way. If you take constant times row I, that replaces row I. So the book, I think of it as this is being replaced by, the book says this replaces. And I apologize for the confusion. Here, if we follow the book notation, it says we multiplied the first equation by 3. So 3 times row 1 is now what row 1 becomes. All right, so again, from last time, if we scale by a non-zero, it's the same equivalent system in regards to solutions. The most important one, we talked about this last time, and it's the one that is maybe not the most obvious, but it's the most powerful. And it says, I can add a multiple of one equation to another equation. So let's suppose I take 2 times the first equation and add it to the second equation. So the first equation stays as is. And if I double the first and add to the second, I would get 9x minus 5y equals 16. What does this correspond to? Well, we see that the rows that isn't being affected stays as is, but the other row changes. So this became, if we use the book's notation, this says that if you take row 2 plus 2 row 1, that becomes the new row 2. So that's how the book would write this. So these are our basic row operations. And this is the list. These are the row operations we're going to do over and over and over again. We're not going to add to this. Essentially, we're just going to get really good at using them. Now, notice we talked about row operations. What haven't we talked about? Channel your inner Lord of the Rings characters. Column. Yeah, we're not talking about column operations. We don't do column operations. We only ever do row operations. Because the key thing here is the rows represent equations. And so the question is, how can we rewrite the equations? And that becomes the row operations. We don't do column operations. So anything that we want to achieve in the columns, we have to get to by carrying out something with the rows. All right. So, any questions to the basics? Let's look at a problem. We have the system, 2x minus y equals 7, x plus 2y equals 4. I don't know if there's going to be nice numbers in the end. I haven't tried this yet. but we're going to solve it. Now, the key here is we want to practice what we've learned. We already know how to solve it from last time. We want to solve it from today's ideas. So we're going to simultaneously solve it sort of in two ways. We're going to solve it using the x's and y's, but also we're going to parallel that by going and saying, let's look at it in terms of what's happening with an augmented matrix. Now, one of the challenges that we have, and you can look at this as a pro or a con, is that there can be many ways to begin. Now, some people are not comfortable with that. They say, no, there should only be one route because then I don't have to think. But thinking's a wonderful thing. We shouldn't be afraid of that. So it's just a matter of saying, all right, we have a choose your own adventure. We have many ways to get to our destination. Not one is necessarily better or worse. We just have to pick. All right. With this in mind, we think about what does it mean to solve? Well, what it means to solve is I want to take that original system of two equations and I want to quote unquote simplify it. That's what math is. Math is a series of simplifications. And here to simplify says, I want to get down to a new system of equations that is so simple, I read off the answer. So I want to reduce it down to x equals something, y equals something, which is not what we have yet. All right, so with that in mind, what are some things we could do? And we have those three operations: swap equations, multiply equations by a constant, add a multiple of one equation to another. Where do you want to begin? You want to multiply the second equation by something? What would you like to multiply the second equation by? Okay, so let's multiply the second equation by -2. All right, so we're going to do the following. Multiply our second equation by -2. Here, this would become -2 times row 2 becomes our new row 2. This is how the book would write it. This is what we're what we're saying. So we get 2x minus y equals -7, minus 2x minus 4y equals -8. Over here, we would get -2, -4, -8 becoming the new second row. Now what? Don't worry, we can always go to this half of the paper, so we can take our time. So multiplying the second equation by -2 makes it, if we think of this, like, hey, we can get some cancellation. So, an idea, let's add the first equation to the second equation. Okay, so that's where we're going. Now, in terms of what we're saying here, we're going to say if you take row 1 plus row 2, that becomes our new row 2. So that's the column operation that we're going to carry out. So our first equation staying as is. Our second equation, 2x plus -2x makes 0x, which we usually don't write. Minus y minus 4y makes -5y. -7 plus -8 makes -15. In terms of our augmented matrix, we have 2 minus 1 minus 7. 0, anything that's missing is a 0 coefficient. 0, -5, -15. By the way, we like zeros. in our augmented matrix. In some sense, we're trying to get down to a very particular form. We'll talk about that in just a second. All right, so that's looking promising. What can we do now? If you just saw this left-hand side, just the system of equations, what would you want to do? You'd like to scale the second equation, right? So let's do that. Okay, so we're going to scale second equation by -1/5. This over here, that says, okay, the second equation is row 2. So we're going to take -1/5 times row 2. That's going to become our new row 2. So we have 2x minus y equals -7. Y equals 3. Scaling by -1/5, it's the same as dividing by -5. So we have 2 minus 1 minus 7, 0, 1, 3. All right. Well, good. Now we know why. Are we done? Well, no, because we need to know x. So now what can we do? Well, plugging back in is not a row operation. I understand your thought process. That's a good thought process, but think row operations. What would we like to do? Well, we already have our y equals formula. Our goal is to get an x equals formula and a y equals formula. So we're like, y equals, yes, nice. So the question is, do we have our x equals formula? No, not nice. This has an x, the problem is it still has a y in it. So thinking in terms of combining matrices together, those three tools we have, sorry, not matrices, equations or rows. In those three tools, what can we do to combine to get rid of that y? How did we get rid of this x? We added the equations. So we can do something similar here. Is there a way to combine these equations to help us get rid of this y? Well, yeah. We can add the second equation to the first equation. Now, in terms of notation, that says if we take row 1 plus row 2, that's going to become our new row 1. So we now have 2x equals -4, because we added 2x plus nothing is 2x, y plus -y is 0, 3 plus -7 is 4. And, sorry, I shouldn't have put that there. Y equals 3. In terms of our augmented matrix, we have 2, 0, -4, 0, 1, 3. Now we're almost there. We want a y equals, which we got. We want an x equal, which we almost have. So what's the last thing for us to do? We're so close. Yeah, scale, because this is a 2. We want a 1. So we can multiply the first equation by 1/2. Okay, so in terms of our notation, that says 1/2 times the first row becomes the first row. So this gives us x equals -2, y equals 3, and over here, 1, 0, -2, 0, 1, 3. So you'll notice these are equivalent to each other. They've always been equivalent all the way down. So we could have solved it, keeping it in terms of equations x's and y's, or we could have just followed the augmented matrix. We would end up at the same place. And at this point, you're thinking, these are 2 by 2s. It doesn't seem like we save anything. We're not stopping at 2 by 2s. We're going to get bigger. And as we get bigger, you're going to be like, I appreciate the bookkeeping that this allows. So, all right, now, notice this matrix on the left, on the augmented matrix, there's a technical term for this. This is nice. Now, why do I say it's nice? Lots of 1s and 0s. And we're going to get into detail next time, but ultimately that's our goal, is we're trying to make as many 1s and 0s on the left-hand side as we can. If we can do that, we win. All right, so let's pause. Any questions here? Any questions about what we did? I know it's in some sense feels very restrictive, but the key thing here is that everything that we were doing last time in terms of elimination can be replicated by these 3 row operations. It's just a matter of getting comfortable with these row operations, which will follow from doing all these problems that we're going to do. All right. So here we have 2 equations. And we're asked, solve these using an augmented matrix. So we'll do both of them. Doesn't matter which order we do them. You want to do the one on the left first or the one on the right first? The right. All right, bold choice. Now, it says augmented matrix. So we're not going to do our parallel thing. We just do that once just to help us see, okay, this does what we think it does. So we're just going to get good at just using these numbers themselves. 2 minus 1, 4 minus 2, and 3 minus 1. Okay, so there's our augmented matrix. Okay, so start thinking about the operations we can do. And our goal is, well, we want 0s and 1s. So a primary goal is try to make 0s. We can get 2 1s by scaling. So how can we make 0s? And I would say, pro tip, try to make that entry a 0. If you're wondering where to start, make that a 0. So is there a way we can make that a 0? Yeah, so what we can do is we can use row 1 combined with row 2. So if we look at it and say, well, the row 1 has a 2. What can I multiply it by so that when I add it to 4, I get 0? So sometimes when I'm doing this, I like to sort of make notes on the side where I say, oh, I'm going to bring this down and add a factor of -2. And this is just my way of saying, oh, take -2 times row 1 plus row 2 to make the new row 2. All right. When we do that, we're not changing the first row, not yet. But the second row, all right, so we get -2 plus 4, 0. -1 times -2? 2. Minus 2? 0. -2 times 3? -6. -6 plus -1? -7. All right. Now, let us pause for a second here and ask ourselves, wait a second, this does not seem right. We're looking at this, and we might be saying, What does that equation say? You're saying, it says 0, 0, negative 7. But remember, these represent something. A row represents an equation. What does that equation say? This dividing line is an equal sign. The negative 7 on the right is easy. What does the 0, 0 tell you? Like 0 times the first variable plus 0 times the second variable. If you take 0 times the first plus 0 times the second, what do you get? 0. Does 0 equal negative 7? No. What? This is impossible. But we don't use the word impossible. We say, oh, wait, this is inconsistent. So if you ever see zeros, and then you see something not 0 on the other side of the augmented matrix, that says you have a 0 equals a non-zero. That's an inconsistent system of equations. If you think about what we talked about last time, in terms of these being lines, what does that represent? It says that these lines are parallel lines. There are no systems. There's no solutions. There are no solutions. All right. So that was the left. Once you get down to a point where it's like, oh, I have zeros on the left equals a non-zero on the right, inconsistent, job done. Well, that means we have to do the other one now. Okay, so we have minus 2, 6, 6. I'll read off the coefficients. 3, minus 9, minus 9. Again, we think about what can we do. Now, one thing we can do is just say, hey, in both cases, the rows have common factors. So I'm going to scale these down. So I'm going to scale the first row by a half, and the second row by a third. So I'm going to do 2 row operations simultaneously. That's right. I'm a wild and crazy guy. And if we do that, we get the following. Negative 1, 3, 3, 1, negative 3, negative 3. So we scaled the rows. All right, now what should we do? Well, we can channel our inner, hey, let's make a 0. So in general, by the way, I do recommend scaling. That helps you keep the numbers reasonable to work with. If you have any common factors, you can scale. If you're seeing fractions, you can sometimes scale, unless you're trying to get, if you're trying to get ones and zeros, sometimes you just have to live with fractions. So here, say, oh, let's just add 1 times first row. So row 1 plus row 2 becomes the new row 2. So negative 1, 3, 3. And what's the new row 2? I'll give you a hint. The first entry is a 0. Also 0. And also 0. Now, is this a problem? It's not a problem like this. It's definitely possible that 0 equals 0. That's actually not a surprise. It's been true for a long time. 0 has equaled 0 for many years. Let's multiply the first row by negative 1. So we get 1 minus 3 minus 3, 0, 0, 0. Now this is as far as we can get. We can't really do any better. So what happens is we say, this reduces down to the equation x minus 3y equals negative 3. Now what does that tell us about our original system of equations? If we used our language the last time, there are solutions, so it's consistent, but I would use the word redundant. The book uses the word dependent. Essentially, you have a duplicate. It's the same equation from before. So, in general, when it comes to the augmented matrix, there are three possible things that can happen. One thing is you can end up with the nice 1001 mn, and then you just read off, oh, the first row tells you the first variable, the second row tells you the second variable. It's consistent, it's independent. You have solutions. You might knock a row out entirely and get all zeros. That's okay. In that case, you reduce down to something where you have a solution, but you actually have infinitely many solutions, and we call that dependent. And the third thing that can happen is perhaps you get to the case where you get a zero equals a non-zero. Usually we don't go all the way down, but we can spot it before we get to there. If we see a zero equals a non-zero, that means inconsistent. What's our basic strategy? How do we get to these? We're going to get into this discussion extensively on the next lecture. But your basic strategy is just saying, I want lots of ones and zeros. Start in the first column. Make it look like a 1, 0. So you scale, you add a multiple of one row to another, maybe you have to swap. And then you say, okay, my first column is good, move to your second column, and then say, what can I do to my second column? And sort of repeat. And you do this again and again. When I say again and again, we're going to build up to where we have more systems of equations. More equations and more unknowns.